Hello, this is Physics Lab 4 Spring Motion. The objective of this lab is to study the motion of a mass connected to a spring through the use of experimental and computed data. The results found when the two models were compared are that the motion of the computer model and experimental model are very similar. However, the computer model does not account for things such as air resistance and thus predicts more motion than was actually seen in the experiment. The fundamental principles being used in this lab are Newton's second law, which states that the final velocity is equal to the initial velocity plus the net force divided by the mass times delta t. And second, we use the energy principle, which states that the total energy change of a system is equal to the work done on that system by its surroundings. In this lab, we have chosen our system to include the mass, the spring, and the earth. Thus, the total energy change of the system is also equal to the kinetic energy change plus the gravitational potential energy change plus the spring potential energy change. These should add up to the work done by the surroundings on the system. For our system, this value is 0 since there are no objects other than maybe air resistance that are affecting the system that are not already within the system. And here are other equations that we will be using during our lab. In order to obtain the experimental data, we use a tracker video, which is shown here. And right here is plotted the y positions versus time, and you can also see the x positions versus time. And then from a tracker, we obtained this data, and the most important parts of this data are right here, which are the oscillation time, which was obtained using the equations in this slide. And then the spring constant was obtained from the oscillation time, and the relaxed length was also obtained from the spring constant in oscillation time. Next, we have our computer model. The most important part of our computer model, like always, is in our while loop, where the position of the mass, or in the model is shown by a ball, is updated. And in order to update these positions, we use forces instead of energies. And the net force is equal to the gravitational force, which is a constant, plus the spring force, which changes as the position of the ball changes. Also in the while loop are the energy changes. And in order to obtain these energy changes, we just use the equations shown earlier in the video, and then we just also, in order to find the changes, delta k, delta u sub g, and delta u sub s, we just subtracted whatever values we found minus the values found in the previous time step. And in order to compare the computer prediction motion to that in the tracker video, we imported a CSV file containing the XY position data from our tracker video into our model. And in the model, the computer prediction motion is shown by a blue ball and the experimental motion by a red ball. And here's our model. And in this video, the spring force is shown by the blue arrow, and as you can see, it changes. And then the gravitational force is shown by the black arrow, and it remains a constant. And right here is the comparison between our experimental model and between our predicted model, and the red is the experimental, and as you can see, like I stated earlier in the video, the distance isn't quite as far as that was as predicted, and this is most likely due to air resistance. And then also we would like to see our energy graph, which we can show by doing a couple things. And in this graph, a delta u sub u sub g is shown with the green, and then delta u sub s is shown with the red, and delta k is shown with the blue, and then the yellow line represents the sum of all of these, which, as you can see, is equal to 0, satisfying the energy principle. And like we just said, the energy principle was satisfied. Now finally, using the data you obtain in Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. Okay, so the X position oscillation period I found to be 1.6524 seconds, and the Y position oscillation period, which I stated earlier, was found to be 1.5194 seconds. This greater value means the ball moves in the same X direction for a longer duration of time than it does in the same Y direction. I'm not exactly sure why this happens, but I know this difference in oscillation period is the reason, that in the beginning of the video, as the ball moves in the negative Y direction, is moving in the plus X direction, but then at the end of the video, after this moving in the negative Y direction, it's also moving in the negative X direction. And that is the end of my video.